Okay. We've started the Hangout, and so you guys are going to start viewing here in a second, and hopefully posting some questions. I just got finished with the pre-AP Hangout, so I haven't had time to totally transition and get documents open. So I'm going to start working on that while you guys get in here and start asking questions. I emailed myself. I emailed myself the documents. There they are. I'm gonna open them up. So we'll have the unit test. So if you guys have questions in the unit test, and I think I have the practice exam, but I believe you guys probably already asked a lot of questions on that. But you never know, right? Might have questions on that too. The only problem would be if you guys ask questions about the worksheets, it'll take me a little while to get those up and going, unfortunately. But I will figure it out. Okay. So, do we have any viewers or questions? No, nothing yet. What the heck is going on? That's okay. So let's do this. The test. I'm not sure. I can't remember what some of the most missed questions were, but I will be happy to cover a few things for what there's going to be some questions in the test. So let me share the atom periodicity test, and I'll make this a little bit bigger. I think might make it easier to see. All right, so mass spectrometry. The deal with mass spectrometry is that as you look at the graph, the y-axis gives you the mass of your particle, your molecule, or your fragment. Excuse me, your molecule or your fragment. And then on the left, it's the overall abundance of it. So sometimes there are numbers at the top of these peaks, and the numbers only mean how much there is of it. Don't get confused and think that the numbers at the top of the peak represent the mass, because it's not. It's the numbers at the bottom that represent the mass. So when you do this, you identify your furthest most right peak as the main molecule. So B would have to be the CH3OH. Okay, you'll notice that there's a very small peak down here. I would attribute that to an isotope. So unless I put a letter on it or unless I speak to it specifically, you can kind of ignore it. But there'll be isotopes in these, but when it's really, really small like that, you can just ignore it. So the furthest most to the right is the molecule. So CH3OH is B. Then as you start moving down, and that was at 30, 31, 32. So you can see that each of these lines is worth 1, so 32. Well, that makes sense because carbon is 12 and oxygen is 16. Together that's 28 plus 4 H's makes 32, so CH3OH. If you drop down one mass unit, oh, I just realized that I'm answering the question that Joanne has. I'm going to go ahead and select that, and that way if people go to that, they'll know that that is being talked about right here at the beginning. So if you click to this point in the video, you might want to back up a little bit because I started talking about it a couple minutes ago. Okay, so if you go down one mass unit, that's like we're moving 1 H. So it becomes CH3O. And then if you go down another unit, now there is no letter at this one. You must have lost another H, so maybe CH2O. And then if you go down this next unit, there's a C there. You probably lost another H, so now it's CHO, something along those lines. And let's see, so that's at 29. So we already said that carbon and oxygen, that's 12 and 16, that's 28, plus 1 H makes it 29. So that makes sense. So we've had B is CH3OH, A is CH3O, and C is CHO. And we go all the way down to 15, which is D, which is that molecule down here. And 15, if we had to look at that, there's no oxygen in it. I mean, you might be able to make the argument that it's an isotope of oxygen, but it is so big. There's so much of it that there's probably not oxygen 15. So I would not accept that. Because you look at this molecule, it makes more sense that carbon as 12 and 3 hydrogens together make 15. Another reason I would not accept oxygen 15 is that the mass of oxygen is 16.00, which means that the relative abundance of oxygen 15 is going to be so infinitesimally small compared to the amount of oxygen 16. So there's no way you're going to get almost 20% of oxygen 15 because it's almost all oxygen 16. So that would not be accepted. It would have to be CH3. 12 plus 3 is 15. Okay, and you can see the answers right there. CH3O, B was CH3OH, A was CH3O, C was COH, and D was CH3. I will not mark you off if you do not include the positive signs for the cation. You should know that they're all cations. It would be the smart thing to do. I don't know what's going to happen on the test if they will go that far, but you should know that. And I did not mark off if you said one was a fragment or one was a molecule. Again, important to know, but will not be marked off. Okay, so that's mass spec. So I've answered the mass spec question. Please ask another question. In the meantime, since we're talking about spectrometry, we should talk about photoelectron spectrometry. So this is free response number 2. And as you go through this, remember they can be in 3 lines or they could be all in the same line. You can do either one. I could do both in the same test, which is very likely to happen. So on the bottom is the binding energy, and the height of the peak is the number of electrons. So you'll notice looking at the y-axis, the x-axis, that the lowest part of the graph is 0 to 10, and then it's 10 to 100, and then it's 100 to 500. So the high energies, that means it takes a lot of energy to remove an electron. This is ionization energy. Binding energies and ionization energy are pretty much the same thing. So the more energy it takes, the electrons that have the highest amount of energy, those are the ones that are closest to the nucleus. They're closest, or the lowest shells closest to the nucleus. So that means it's the 1s block or 1s subshell. So that means up here, A would have to be 1s2. Makes sense. Then as you start getting to lower and lower energies or decreasing energies, you're just gonna move to whatever the next one is. So 1s2, the next one's gonna have to be 2s2. And then the next one will be the 2p6, further out, 3s2, and then 3p1. And so when you look at that, if you were to look that up on the periodic table, you would identify that as aluminum and give its electron configuration. And so I think that's pretty straightforward. I think that many of you are maybe starting to get a hold of that. But just definitely being able to identify the peak, identify which subshell it's in, possibly be able to identify which element it is. That'd be important. All right, I see that Ephraim has asked a question about 3A and 3B, which I'm assuming is the free response, 3A and 3B. So if I scroll down, I was in 2, I can scroll down to here, 3A and 3B. This is all about just using the equations. And I mean, I'll provide you with the equations or provide you with the constants. So I'm going to, I mean, you can see them here, but I'm going to go ahead and do this on my bamboo paper, because if you process, it might be a little bit easier to solve it, or, you know, for you to understand the process to solve it. Okay, so we are looking at essential skill number 3A. We'll do that one first. It says a certain element emits light with a wavelength of, so you're given a wavelength equals 563 nanometers. Okay, that's the wavelength. For A, you have to find the frequency. Frequency is the nu, right? And you're given two equations. C is equal to wavelength times nu, which is wavelength times frequency, lambda nu, wavelength frequency, and you're given the other one. E is equal to h, which is Planck's constant, times frequency. So if you're looking for this and you're given lambda, you must be going to use this equation, right? Which is C is equal to wavelength times frequency. So you just, and C is a constant. C is equal to 3.00 times 10 to the 8th meters per second. And since you're solving for the nu, the frequency, nu is equal to C over wavelength, okay? So you plug in 3.00 times 10 to the 8th meters per second divided by wavelength, which is 563 nanometers. Okay, now we have a problem. We see that these units do not agree, so we're going to have to change this. So I'm going to go ahead and erase this right now, and we're going to switch that over. We're going to change it. In conversions, we just use bridge, 563 nanometers, and we know that 1 meter is equal to 1 times 10 to the 9th nanometers. That's nano is 9 usually, as far as a prefix. And that's 1 billion nanometers in 1 meter. So when we do this math, we end up with 5.63 times 10 to the negative 7th meters. So I go back to the problem and I type that in, 5.63 times 10 to the negative 7th meters. And I know that my meters are going to end up canceling out, leaving me with 1 over seconds. And when I plug all that in, my frequency ends up being 5.3 times 10 to the 14th, which makes sense because that's 8 divided by negative 7, which is 8 minus negative 7, which is 15, and you got 3 divided by 5, which is a number less than 1. It's fine, all the math will figure it out, which is 1 over s. And if you'll remember, by the way, you might see this on the test, 1 over s is the same thing as s to the negative 1, which is the same thing as hertz. So you might see it on the test, you might see it in problems, whatever. And then for B, the question is find the energy. So energy was the one we didn't know. And now we're going to be using the E equals H times V. And we found V, and H is a constant. H is equal to 6.63 times 10 to the negative 34th joules times seconds. So E is equal to 6.63 times 10 to the negative 34th joules times seconds times the frequency, which we got from a previous problem, 5.3 times 10, wow, the 10 writing is awful, 10 to the 14th, 1 over seconds. And so we just multiply it out, and the seconds cancel out, leaving you with joules, and E ends up being equal to 3.5 times 10 to the negative 22 kilojoules. And probably when you solve this, since it's in joules, it's going to actually be, 3.5 times 10 times 10 to the negative 19th joules. But it asks for in kilojoules, so what you have to do is do your bridge and remember it's 1,000. You're going to divide by 1,000 because it's 1,000 joules in one kilojoule. So when you divide by 1,000, that's how you get the negative 22. And that's how you do number 3. All right, moving along. Joanne asked about 4B and D. 4B and D. All right, so let's look at that on the test. Where is that? Oh, nice. Okay, these are the reasoning questions, justification, and all that good stuff. So 4B says, is the radius of Mg2 plus greater than, equal to, or smaller than the radius of magnesium? So the things that I feel like are the most important are mentioning that what do they have in common first? Well, I'm going to do a little bit of highlighting here. Magnesium and magnesium have the same number of protons. So you would say something to the effect of magnesium 2 plus and magnesium have the same number of electrons. However, magnesium 2 plus has 2 fewer electrons. It in fact has lost an entire shell, so it has 1 less shell than magnesium. So because of the effective nuclear charge, the magnesium 2 plus would have a greater effective nuclear charge and would pull the electrons tighter, making the radius of magnesium 2 plus smaller than magnesium. So this is my key. However, it doesn't say, like, I don't like this altogether because it doesn't talk about magnesium 2 plus has a greater effective nuclear charge. I expect you guys to use the terminology. I want you to use the term. That is what the readers are looking for. I haven't updated my key since last year. I just had it, and I was just remembering it. But you have to talk about that stuff in every question. Okay. D. The first ionization energy of beryllium is 900 kilojoules per mole, but the first ionization energy of boron is 800 kilojoules per mole. Explain. You must discuss both substances during the point. Good. Okay. So beryllium and boron. So you would say something to the effect of boron has 1 more proton than beryllium. So while you might expect it to have a stronger effective nuclear charge, the extra electron that's added with the proton is the first electron added in the 2p subshell. And that 2p subshell causes there to be a little bit more repulsion, or you might say that there is some shielding, that the S shields the P slightly, making that electron somewhat easier to remove. So it's good to talk about, again, we're talking about shielding. Remember, it's either shielding or effective nuclear charge, or both. And in this case, you know, I think the shielding kind of comes in a little bit. Honestly, that's probably not my favorite question. That was in the test a number of years ago. I don't know if they're going to come back to that one and talk about shielding between the subshells, but it is important to know that there is a little bit of shielding between the S and the P. So that's 4B and D. So I will click that one. All right, let's see the next question on the list right here. Oh, I see a few. Oh, so Aria, I'm going to select your question right now. Yours is on the free response number 1, and let me share. I actually covered that at the beginning of this review thing. I'll just show you the page really in the Bamboo, but it's in the video. So if you want to go back and look at it, but I'll show it to you right now. Free response number. Oh, did I? Oh, it wasn't in the Bamboo. Dagnabbit, I just showed the paper. All right. I don't want to go through the whole thing again, but I will talk about it briefly. Okay. Basically, just to say real quickly, again, you need to go back and watch the beginning part of this video, that the furthest most high peak is your molecule. And you can look at the bottom. The bottom gives you all of the masses. And then if there's a number at the top, it's most likely referring to the relative abundance or intensity, meaning like how much you're getting out of that. And so for the B one, that one would be the molecule, and then every other one would be a fragment. And if you look at the masses, this one says 32. That is the mass of CH3OH. And then every peak as you move down, it's everyone that drops by 1 removes a hydrogen. And if you drop all the way down to D, it's going to be, because then carbon's 12 and hydrogens are all 1, 12 plus 3 more gives you 15. So that means that's why D would have to be the CH3. Okay, so again, go back and look on that one. Read the beginning of the video for a more detailed explanation. Okay, we have Christine Cho. You had a question on 4C. So I covered 4B and 4D. 4C is right in the middle there. You have calcium 2+ and chloride. Those two ions, they're isoelectronic, but the radii are not the same. Which ion has the larger radius? Explain. You must discuss both substances to earn the point. This one is just made to be explained this way. You would say that isoelectronic means they have the same electron configuration, or which means they have the same number of electrons. Okay, so the same number of electrons, but calcium 2+ has more protons than chlorine 1-. So it has a greater effective nuclear charge, meaning it pulls the electrons closer and makes the ion radius smaller. Okay, so that is 4C. Again, you're comparing electrons, you're comparing protons, you're comparing shells. Because it has the same number of electrons, it's the same shell. There's no shielding difference. It's all about the protons then. Okay? So hopefully that answered 4C. But yeah, effective nuclear charge. Let me just highlight that. Calcium 2+ has more effective nuclear charge because it has, well, you talked right here, calcium has more protons, or chloride has fewer protons. That's what that one's all about. Okay. Jordan Noble is asking a question about multiple choice number 2. So, what is the number of half-filled orbitals in an atom of chromium? Oh, this one's a fun one. You probably don't remember that copper and chromium are exceptions on our electron configuration. So, go to the next page and get that going. And I'm going to do the orbital notation, and I'm going to do it in its noble gas configuration to make it easier. So we've got argon, yay, and then the 4s, okay, and then 3d. Let's see, 1, 2, 3, 4, 5. Good. All right. So 4s for chromium, you would expect this. You would expect the s to be filled, and then the d's to be like this. Okay. So chromium is 4n on the electrons here. So that gives us only 4 half-filled electrons. However, chromium and copper each borrow an electron from 4s because atoms are more stable with their lower energy being half-filled or fully filled. So it's gonna, since it borrows that electron from the s, you now have 1, 2, 3, 4, 5, 6 half-filled orbitals, which means that the answer would be C. Hopefully that answered that for you. All right, multiple choice number 10. Aria wants to know about multiple choice number 10. So share the test again. Okay, atoms of an element X have the electronic configuration shown above. The compound most likely formed with magnesium is, all right, so let's go back to the bamboo paper and write this out. Okay, so we have 1s2, 2s2, 2p6, 3s2, 3p3. So if I followed all this out, I could either go straight to the 3p block and look for the third element from the left, or I could count the number of electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. And I looked at the table, and I would see that that element that it's describing, the electron configuration, if I said which element has this electron configuration, you would say, oh, that's phosphorus. Okay, and then I would say, okay, that sounds good. Now, could you please tell me if phosphorus forms an ion, or let me do this, how many valence electrons does phosphorus have? And you would say, oh, it has 5 valence electrons. So, excellent. I would say, okay, is it going to gain or lose electrons to form an ion? And you would say it's going to gain 3 electrons to fulfill the octet rule to be stable at 8 electrons. So that means that phosphorus as an ion, the phosphide ion, has a 3- charge. Now we have magnesium, and I'd say what kind of ion does magnesium form? I'd say, oh, it has a 2+ charge. So magnesium, 2+, phosphorus, phosphide with a 3-, and we do swap and drop, and we end up with magnesium 3, phosphorus 2. So they just gave you one with an X instead of a P, even though that's what it's supposed to be. So magnesium 3, X2, which means that your answer is D for that multiple choice. Okay. Done. All right. Free response to C and D. So that's Jordan has them for both. So what I'm going to do is I'm going to select that right now. And we actually already kind of answered this one. So I'm going to tell you that you can go back in and, oh, there is no D. There's just a C. Oh, we didn't do C. I gotcha. Okay. So let me share the... Oh, we did do D. I'm sorry, because that was the one that I added at the end. Okay. So C was why is the energy for peak B so low? And we labeled them here A, C, B. And so in my earlier explanation of this, I explained that the height of the peak correlates to the number of electrons. So, and it even has the number 1 on it. So that tells you there's only 1 electron in that. And it is the lowest energy, which means that it is the furthest from the nucleus. So that is its last valence electron that was added on there. So if we were to go through this, we would have 1s2, 2s2, 2p6, 3s2, 3p1. So that's aluminum. That means that there's only 1 electron. So what is this? This is a horrible explanation, making the energy so no. Did I write that? I sure hope that's not how I graded your peak B. But why is the energy so low? I'm so sorry. No, that's right then. Oh, I must be tired. Peak B is shielded by lower energy, right? Gee whiz, very tired. My apologies. The peak B is shielded by the lower energy levels, making it easier to remove. That's why the peak is so much lower in energy. Forget the number of electrons, it's the energy. So it's low in energy. Okay, D, the question D, I had it typed up, but I didn't put it, of course I didn't put it on this key, so I can't show it to you right away. But I can tell you it was about, let's see, I can type it in. D was about, given the evidence from PS, why do we have to revise the Bohr model? And the reason that we have to do that is PS shows the different subshells. Shows the energies of the different subshells. Whereas the Bohr model indicates that all electrons in a shell are together and have the same energy. Something along those lines. That's basically what I was looking for there on D. And we talked about that in class. Bohr model, all electrons for a shell are in the same shell. There's no difference. Whereas in the PES, it shows that S, P, D, and F all have different amounts of energy, which means that they're not all together in one shell, that they're actually broken out maybe different distances from the nucleus, that they have different energies to remove them, that and we kind of mentioned above that there's some shielding between, there's slight shielding between different subshells. So that was D. That's what we're looking for. All right. So that is your answer to D. C and D on for response number 2. And Efrain, thank you for explaining about being able to go back and look at questions in the past. That is very helpful. So I'm going to select that one and say done because you did that. All right. Multiple choice number 12 for ARIA. All right. The elements in which of the following have most nearly the same atomic radius? Aha. Okay. You know what I'm going to do is, I'm thinking about it, maybe I can, I'm going to pull up a periodic table. This image on the web browser, and so you guys can just look at them. Just a simple one. Okay. All right. Okay. So you can see. So let's see. Oops. The choice A gave us beryllium in the S, in the 2S, and then boron, carbon, and nitrogen in the 2P. 12, B choice gave us neon, argon, krypton, xenon. Obviously, they're in different energy levels. They have different shells. They are definitely not having the same atomic radius. C gave us magnesium, calcium, strontium, boron. Obviously not. They have different radius. And then D, chromium, manganese, iron, and cobalt. So you're comparing, really, if you narrow it down, you're A or D. And the difference is that in D, they have a 4s that's outside and a 3d's below, which means that the actual radius difference when you keep adding electrons in the center like that is not going to be very great. Whereas when you add it from 2s to 2p, it's adding a subshell. It's adding like another layer, because P is a higher energy than S, you would actually get a greater difference in size. Instead of when you add transition metals in the same energy level, they're actually below the outer energy level, and so the change in size is not very great at all. So that's why D would be the right answer for the multiple choice of number 12. There's actually some really cool stuff involving, if you start looking at, let's see, which ones are there? There's some elements, I want to say, in here, like the osmium, iridium. Oh, I'm forgetting which ones they are. But when you start adding into the F orbitals, this must be it. Like yttrium and lutetium and zirconium and hafnium, they have some very similar properties, because when you add to the F, you are not increasing the size of the radius hardly at all, and they have the same number of valence electrons, which is basically 2. They have some similarities there, and so the properties of those elements are really, really similar, even more than you might expect, given the fact that they're in the same column. They really are quite similar. Okay, so that answers multiple choice number 12. All right. So we are cruising along. I very much appreciate that you guys are asking a lot of questions. This makes this a lot easier. While I'm waiting for another question to pop up, there is a question that, oh wait, here's one. Which website was the periodic table you used on? Oh, this website right here. Oh, it was just, I just typed in periodic table and did a Google search for images. And this one was at middlebury.net, op-ed periodic table.jpg. I just typed in here, I typed in periodic table, and then I clicked on images, and it was the second choice, or maybe it was the second link, or the second whatever it's called. I can't even think straight. So that's all I did to get that periodic table. It's not my own periodic table. I just quick looked it up. Easy enough. Oh, I know what I was going to do. Okay, so I was going to shift again. And I want to talk briefly about, where is it? Oh, there we go. So number 11 on the multiple choice, that when you get these, you get the ionization energies. They're called successive ionization energies. That wherever your big jump is, right, that's a noble gas. So the biggest jump happens from when you get 1,700 to 14,000. Obviously, that's an enormous jump, which means that this is your noble gas. So when you, that's your, and that was the third electron removed. So the second electron removed means that you are adding an electron. So when you add an electron, you're going back the other way. So you wouldn't go to the halogens, you would go to the alkali metals. Okay? And then the next one would be, so you're adding to it. So let's say you went, if this was the third, is that maybe helium? And so if you added 1 to helium, you would make it lithium, right? If that was helium, and you would be adding 1. You're going up in number. That would make that lithium. The next one would be the alkali earth metals, and so that would be, what is it? Beryllium? No. Yes, beryllium. Sorry. Beryllium. I guess I could have looked at the answer to the question. So when you work your way back like that, that's how you figure out the answers. That's how you figure out the answer. When you're working your way back, you're adding 1. You're going from, oh, well, that was 2. That means this is 3, and this is 4. You're adding up that way. Okay. I think that people struggle sometimes with successive ionization energies. And you'll notice that there's a ton about ionization energies between this and PES and getting your ions, and then, you know, figuring out your electron configurations, noble gas configurations. All that's really important. I guess this is the key. It doesn't really matter. I just leave that on there. All right. Other questions that you guys might have? No. Let's see. Make sure you know your violation, off-bow principle, Hund's rule, Pauli exclusion principle, identifying your valence electrons. You guys remember that only the s and p orbitals together give you the valence electrons. That's important. Identifying if something is an excited state or a violation of off-bow. That's kind of an interesting one. That question that if I could go back for a second, the question that was asked out, that I think Ephraim asked about the numbers. Let's see. For frequency and wavelength, identifying that relationship here, because that's the speed of light, that's a constant. So the relationship between wavelength and frequency is an inversely proportional relationship. That as the wavelength goes up, the frequency goes down. And of course, as frequency goes down, so does energy, because they are directly proportional. So being able to identify that would be good. Let's see if there's... I think I've hit most of the things. This the justify question, the explain and justify, paramagnetic versus diamagnetic. I think I've got it all. I think I've hit the major things. As long as you've studied your practice test and your test, we've done this review, you kind of go back. Oh, here's a question. Number 5 on the multiple choice. Sure. Let's look at number 5 on the multiple choice. Represents a violation of Hund's rule. If you remember the Hund's rule, so off-bow principle A, off-bow, you got to do the lowest energy levels first. Hund's rule, you have to put 1 electron in each orbital of a subshell before you can add a second one. So B is the violation because you didn't add 1 to each orbital before you added the second one. Pauli exclusion principle, violation would be they'd be pointing the same direction. You can't have electrons that occupy the same space. They can't have the same. With electrons, you either know their location or their speed, and they can't be in the same location. And what this is saying is that there's the same location, occupying the same space. So you can't have that. Good. All right. That was number 5. Now, Arya would like to know about multiple choice number 1. Which of the following represents the ground state electron configuration for the cobalt-2 plus ion? So the actual electron configuration for cobalt would be would end in 3d7. Let's do this. Let's do let me share the bamboo paper for a second. I think it'll be easier if I just kind of write this out. Okay, so cobalt is normally a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Okay, that's cobalt. Now, if we want to do cobalt 2 plus, the temptation would be to say, oh, I just removed the 2 off the end and end up with 3d5. No. When ions or when electrons are removed, they're removed from the outermost energy levels. Ionization energy is removing valence electrons. So the S and P are your valence electrons. So you're removing the 4s2, which means that your answer is 1s2, 2s2, 2p6, 3s2, 3p6, 3d7. Sorry about the overlap there, but that is how you would come up with the right answer there. So whenever you create ions for transition metals, you remove the S valence electrons first before you start removing D. Like if it had been cobalt 4 plus, it would have been 3d5, but you would have removed those 4s2s first. So hopefully that answered your question. So, all right, Arya. Ephraim, you're a funny guy. Probably it's harder for some people because of the explanation part of it A little bit less math. On a completely unrelated, oh, Jordan, all right. Why are atoms with 110 plus protons unable to support itself for an extended period of time? It has to do with the stability of the atom. Like the protons repel each other, and as you get a lot of protons up there, you need more neutrons to give up, because there's that the concept of mass defect. It gives, the neutrons give up mass to bind the protons together. So you need the neutrons in there to give a little bit of space, to get the optimal distance between the protons, to give up some binding energy. And you get so many protons in the same space, it's just hard to get the right ratio of protons and neutrons. There is supposed to be like an island of stability, and I don't know how they found that. They talked about it in the video at one point, but I don't have a lot of the explanation on that level, the quantum level, with the relationship with the protons with each other, and why the ratio of neutrons doesn't work as well. I mean, the ideal is that 1-to-1, which is why you have carbon and nitrogen and oxygen, some really stable elements with a 1-to-1 ratio. And then once you get above that, I mean, they're stable. They're just not, maybe not as stable or not as common, especially above 83, obviously. Okay. Joanne, is it? Yes, I can help you with a pre-lab question. I would love to. Yes, I will help with a pre-lab question. If you would give me which pre-lab question you're talking about, type that up. Give me a second to, well, maybe if you ask it, and then I'll see if I need to look up. I don't know if I need to look up. Or type in your question, and then I'll see if I have to look it up, or if I can just answer it off the top of my head. We'll see how that goes. Go ahead and ask your pre-lab question. Joanne? Are you having a hard time figuring out how you want to type it up? Are you having difficulty, Joanne? Well, oh, well, maybe both 1 and 2. Oh, I thought you were going to type up the actual question. Okay, give me a second to, let me see if I can. Our lab that we're doing is determination. Oh, this, okay, so the tin oxide lab. Let's see, when's the most recent one that I have here? It's it. Pre-lab. Write 2 balanced equations for the formation of a tin oxide from metallic tin and oxygen with the reaction producing tin oxide and tin SNO2 for each separate equation, and look produced for all products. From the balanced equations above, what are the percentages of each on the 2 compounds? Okay. I kind of ran through that pretty quickly. Why don't I share the screen? Oh no. I think I just made it smaller. Oh no, there it is. Okay. Guys, Gotcha. Okay. Let me just, you know what? Now that I'll just go ahead and share the bamboo paper. Okay. So when you are, well, let me select these questions actually too, so people want to look at it. Formation of tin from metallic tin and oxygen. Okay. So basically what you're saying is you've got tin plus oxygen yields tin oxide. Okay, so, but the question is oxygen as a gas, you have to remember that it's diatomic, so it's SnO2, which means that tin, if it forms tin, SnO just like that, then this tin must have been a 2+, because we know that oxygen had to be a 2-. So this was the product for 1. So this is definitely it. So now we just have to do the balancing, which makes we have 2 right here and 2 right there. If we're making SnO2, it gets all of a sudden immensely easier. It's just like that. This tin is now SN4+, right? Because with swap drop, it's ionic, it would have to be. Now, to determine the percentage of each element in the 2 compounds, if you guys remember that, that was that mass percent we did, where you have the mass of tin, which, look it up real quick, 118.7. So 118.7 about, let's just, I don't remember what it is entirely, divided by, so if it's the SNO, it's 118.7, let's see, 118.7 plus 16, which means it's, oops, oh, I hate when I do this. That was still there? Okay. Okay, 134.7 times 100 will give you the percent of tin in tin oxide. And then, you know, doing the oxygen would just be 16 over 16.00 if you want it. We should do it right. Times 100 equals the percent tin, or percent, oops, oxygen. Haha. Just kidding. Percent oxygen in tin oxide. And then if you're doing the tin, the SNO2, then it is 118.7 divided by 150.7 times 100 gives you the percent tin in tin oxide, SNO2 more specifically. And then you do the same thing, the 16 divided by 150.7 times 100 gives you the amount of oxygen in SNO2. So that's how you would identify the percentages, how you would figure out balancing the equations for the tin, metallic tin plus oxygen gas to give you those formulas, and then how you'd find the percent oxygens, or the percent elements in each compound. Okay, and so that would answer all of those 3 questions. There were just rewordings on that. All right, Ephraim, what is your policy on grade bumps for AP test? I'm assuming you mean the AP exam itself at the end of the year. And if you get a 4 or 5, I give you a grade bump. That is the policy. Of course, you have to pass the class. You can't get the grade bump if you don't pass. But if you have like a B and you get a 4, you get an A. If you get a C and you get a 4, you get a 5. A B, give you a 1 grade bump, I believe. All right. Any other questions? So when you guys come in tomorrow, we're going to jump right into the lab. And I have most of the stuff out. You guys will just have to come in and get into your lab groups. I think that I'll let you guys pick your lab groups this time. I need to remember to change the lab groups for next time, but You guys get to pick them, or you've already picked them. And I think that I've used, so we've got a hot plate in the hood, and then we'll have Bunsen burners. And you guys need to make sure that you very careful with this. And actually, I'm not going to use the crucibles. I'm just going to use the evaporating dishes or whatever they were that I had. I think I did find it to be easier. And since I'm not seeing any other questions, and it's almost 10 o'clock, oh, no F- to A+ for me. That's too bad, Ephraim. No. Okay. Since there aren't any other relevant questions to the material at hand, the lab tomorrow or the retake that we're doing on Tuesday morning, I think that I will sign out for the night, and you guys will hopefully are close to finishing up and being ready for your lab tomorrow. So I look forward to seeing you all tomorrow. Thank you very much. Good night.